and thank you so much for joining me on this video about the energy systems. So this is our final video in the level 3 series of videos on our anatomy and physiology, and it'll be drawing together a number of topics that you've looked at previously and hopefully help you to do a little bit of revision. You've already been looked at energy systems at level 2, so it's well worth having a read up of that first of all. Don't forget that your manuals will also supply a lot of information, as will the revision tools online. There's the interactive revision tools on Canvas. So let's get going, see what we've got. So by the end of today's session, you're going to be able to identify which energy systems are used according to type, duration and intensity of exercise, and how these all interact. Secondly, you're going to be looking at the byproducts of the energy systems and how that can affect performance. And finally, explaining the effects of different types of training on the production of fuel for exercise. Before we dive in and really get started, I want you to get a piece of paper maybe and just have a think about some of these questions before we start. So if you want to pause the video, then that might be a good idea, and just jot down a few notes for each of the following points. So what are the 3 main energy sources we get from our food, and what are the different things you can remember about each one? So if you have done nutrition, this should be easy for you. If not, don't worry, we're going to go through it in a minute. Secondly, what are the 3 different muscle types? So this goes back to the muscle contraction video and information that we went through. And what can you remember about each one of those? Because that will also tie into what we're doing today. And from previous learning, what are the 3 energy systems? Can you remember their names or maybe anything about them? So just take a few minutes to have a think about those to get your head in gear before we move on. Okay, I hope that was a useful exercise. So let's have a quick recap of these fuels that we were talking about. First and foremost, carbohydrate. That's the fuel that will always be used first. So if you've done nutrition, you'll remember that it provides 4 kilocalories per gram. We should be having about 50% of our daily calorie intake should come from carbohydrates. It's stored in the form of glycogen. So we do have blood glucose, but actually our muscles and our liver hold those glucose stores as glycogen. And the process of converting glycogen back into glucose for use for the energy system is called glycogenolysis. That's glycogenolysis, the conversion of glycogen stored in muscles and liver back into glucose. Secondly, we've got fats, and that provides more energy per gram. So that's 9 kilocalories per gram. And that shouldn't comprise of more than 35% of our daily calorie intake. And that is stored beneath the skin and around our organs as adipose tissue, fatty tissue. And fat breaks down into 2 components, which are triglycerides and breakdown of triglycerides. It breaks down, into fatty acids. And that process is known as lipolysis. And then finally, protein. Now, protein isn't usually used as a source of energy as such, as a fuel, because we need it predominantly as a building material for our growth and repair of our tissues. And like carbs, it provides 4 kilocalories per gram, and our intake is very much going to depend on our our exercise and levels during the day. So if we have lower energy requirements, lower activity levels, we should be consuming lower levels of protein, But if we're doing intense exercise and heavy body, weightlifting and things, we're going to be looking at consuming higher levels, up to 1.8 grams of protein per kilogram of body weight. More of that is covered within the nutrition module. This is just an overview. So there is proteins break down into amino acids. Then amino acids can break down into glucose in the liver. And the process of doing this is called gluconeogenesis. But the body only breaks down protein to provide a source of glucose for the body when all the other energy stores are pretty much run out. So when there's insufficient carbohydrates left, because once we start breaking down muscle, we're looking at once we start breaking down using protein, we're often looking at a breakdown of our muscle tissue. So it's one to be aware of. Gluconeogenesis, the breakdown of proteins into amino acids, then amino acids into glucose. So there we go. So we've had a quick look at the different nutritional sources of fuel. Our carbohydrate stores, which provides our glucose, our fats, which provide our fatty acids, and our proteins, which provide our amino acids that can be converted into glucose as well. And the purpose of all of those is to be able to produce enough adenosine triphosphate, ATP, and that is our energy currency of our body that allows our muscles to work, that provides us with the energy we need for living. And the reason we need energy sources from those fuels is because energy is released when ATP is broken down. One of the phosphate groups is released, causing it to break down to ADP plus P. So, and in that breakdown of ATP, energy is released, and we need the fuels to recreate ADP back into ATP. So there are three ways that the body does this conversion of ATP to ADP. And the first one is the phosphocreatine system, otherwise known as the ATP-PC. Sometimes you see it written as ATP-CP, phosphocreatine or creatine phosphate. So it can be either way around, but it's the same thing. The second system is your lactic acid system, otherwise known as anaerobic glycolysis. It's an anaerobic, happens without oxygen or just a lactate system. And the third one is the aerobic system. That's going to be with oxygen. You'll probably remember these from your level 2. Phosphocreatine, lactic acid, and aerobic. The first two are anaerobic. Third one, obviously, is aerobic. And the one that the body chooses is going to depend on your levels of exertion, how hard you're working, your fitness levels, and how long you're carrying out that activity for. So there's a little image at the bottom that shows you the structure of adenosine triphosphate. And the little red lines between the P, those are the phosphate groups, are the ones where energy is stored. So when the end phosphate's broken off, energy is released. And here's just some images. So we've got our ATP-PC, as you can see there from doing some heavy weightlifting, maximal effort. Anaerobic, our lactic acid, anaerobic glycolysis, sort of shorter duration activities. And our aerobic, our long duration activities. I thought this was a useful one to put in at this point, just to see how they interact, that they're not completely separate from each other, but they kind of cross over. So starting on the graph from the far left, the first thing we use is our very limited supplies of ATP that's actually stored in the muscle, literally lasts a couple of seconds. So as soon as that's done, then your ATP-PC or CP system here takes over up to approximately 10 seconds. In some places where you read it says it goes on for longer than that, but for the purpose of this exam, let's say up to about 10 seconds. And then you can see the green line is your lactic acid system. So and that starts taking over once your ATP-PC has run out, and that goes on for about 2 to 3 minutes. And then lower down, you've got that aerobic system, slow to come in, but just ongoing. So there you can see how they all interact with each other. And again, another way of looking at it at the bottom, your ATP-PC starts at the very beginning, then the aerobic glycolysis takes over, and then your anaerobic glycolysis takes over, and then your aerobic system kicks on for the much longer duration. Okay, so we're going to look at each one in turn now. So the first one is our phosphocreatine system. And as you could see from the pictures, this is our real high intensity, short duration activities lasting up to about 10 seconds. It's anaerobic, uses phosphocreatine as a fuel, and the energy to convert, as I say, ADP to ATP, supplied by the creatine phosphate and broken down by the enzyme creatine kinase. So you can see at the bottom, CP, the same as PC, creatine phosphate breaks down ADP in plus creatine plus phosphate, and then that combines back into ATP plus your creatine. So another image of how it works. Here on the left, you've got your phosphocreatine being broken down by your creatine kinase to create creatine, energy, and phosphate. And that phosphate and energy allows the recoupling of ADP back into ATP. So let's look at how long this system lasts for. As I mentioned before, we've got very limited ATP in the muscles, so this is accessed first, but only lasts a couple of seconds. We cannot store much ATP. We've then got some stores of creatine phosphate, again limited. These are stored within the muscle cells themselves, but we get energy release from the breakdown of creatine phosphate is used to reattach that free phosphate to the ADP to reform ATP. So these are just different ways of explaining the same thing. So because those supplies of creatine phosphate are so limited within our muscles, you've only got enough for that 10 seconds before supplies are used up, and then you're going to need quite a significant amount of time to recover those supplies back up to 100%. So a good few minutes it takes to get those creatine phosphate levels back up. So significant recovery time. So here we're tying in the kind of muscle types as well, because this system is going to use those fast glycolytic, those fast twitch muscle fibers. Are going to use the phosphocreatine system. If you remember, those are the white fibers. So they've got not many mitochondria, so they've got low aerobic ability. So they're going to need to use an anaerobic system for them to work. Those fast twitch are suitable for short bursts of very intense activity. So it means that the best energy system for them to utilize is the phosphocreatine. So they match up there. Fast twitch match with your ATP PC system. So let's think about training, the phosphocreatine system and adaptations to training. So as you train this system, you actually can train your body to store higher levels of creatine phosphate and ATP, because if you're building your muscle, if you have hypertrophy of your muscles, you've got more muscle, so more ATP can be stored and more creatine phosphate can be stored. The more you practice these particular training methods, you're going to get improved motor unit recruitment, and we know that's going to result in improved power. You're going to get increased production and release of creatine phosphate from the liver. So again, that's going to improve your creatine phosphate system. And overall, the system training is aimed at improving strength, power and speed, and you're looking at that hypertrophy, increasing the size of specific muscles. So looking at the kind of training that you're going to do for this, if you want to train the phosphocreatine system, it needs to be exercises that are performed at maximal intensity, and that's right up at 95 to 100% of your ability. Short duration activities and exercises such as that high weight, heaviest weight possible for just a few reps, even just 1 to 2 reps is going to be your sort of real hardcore phosphocreatine system training. So high weight, low reps, very short sprint interval training, say your 100-meter sprint, full maximum effort, or running up hills, stairs, where you're putting maximum effort into it for a very short period of time. So let's move on secondly to our lactic acid system. And if you remember, it's also known as anaerobic glycolysis. So we know it's an anaerobic, it doesn't use oxygen. glycolysis. It's going to use glucose, the breakdown of glycogen into glucose, as the fuel. So this is the system that's used after your ATP-PC system runs out. So this is more moderate to high intensity, still quite high intensity, but not as high as the previous one, short duration. And this starts to maximally work from about a minute or 90 seconds up to about 3 minutes. And what this does, it prolongs the body's ability to carry out that high intensity activity that you started with the ATP-PC system. It's anaerobic, like the ATP-PC. They're both anaerobic, and the energy is supplied by, it says glycogen here, it's the glucose, it's the breakdown of glycogen into glucose. It produces lactic acid, and this is where the problem comes with the byproduct. So because it's anaerobic, this is what happens. You get your ATP plus your phosphate and your glycogen. Glycolysis happens, but because there's no oxygen, you get ATP and lactic acid. So what happens is without the oxygen, the glycogen is converted into pyruvic acid anaerobically, and that produces the ATP. But the pyruvic acid then combines with hydrogen ions to form the lactic acid, and that's what we know. So you can see in the image there, the breakdown of glucose provides the energy for ATP to be reformed, but we create lactic acid as a byproduct. It's not a terribly efficient system because it requires a lot of effort for quite a low yield of ATP, so definitely not an efficient system. And as we get that buildup of lactic acid in the blood, we get that cramping and burning sensation, which is the thing that impedes our performance and will force us really to slow down. So as I say, this is sustainable for up to about 3 minutes. And it increases once the ATP system begins to run out. And once you get to about 30 seconds, you're looking at getting pretty much all your energy from that anaerobic glycolytic system. Now, I'd mentioned about how the amount of lactic acid in the blood increases, and you might have heard of the term OBLA, which is the onset of blood lactate accumulation. And this is your anaerobic threshold you reach in exercise when you're producing more lactic acid than your body can clear from your blood. And this is your OBLA, your anaerobic threshold. And this is at about 4 millimoles, when the lactic acid in the blood reaches about 4 millimoles. And then that's when the onset of that burning and the pain, which causes you to physiologically, you have to slow down. And this is directly related to intensity. So the more intense it is, the sooner you'll reach that OBLA level. So it might be that you want to train the lactic acid system if you're doing particular activities or you are involved in sports that require the lactic acid system. So with training, with the right amount of training, you're actually going to be able to improve your tolerance to that discomfort of the lactate buildup, so you can cope with it better. You're going to increase your storage of that glycogen, which is your fuel for the lactic acid system. You're going to have improved mechanism of that anaerobic glycolysis, and your body will be able to increase the rate that it removes the lactic acid, and this has the overall effect of increasing that point of OBLA, so you can do more exercise before you reach that anaerobic threshold, when you've hit that point where your body cannot clear the lactic acid fast enough. So this is where you're looking at training your muscular endurance and strength, and when you're looking to try and overload the system to produce those large amounts of lactic acid to try and improve those things we've just talked about, improve that subjective tolerance and improve your body's ability to cope with it. So there are probably a number of things that you'll already know that are going to use a lactic acid system, and the percentage that you would want to train someone at or train yourself at if you're looking at training the lactic acid system is about 75 to 85% of your max ability. So the kind of activities that are going to include that are going to be things like a 400-meter run or canoeing against a current. If you think about the gym setting, if you think about resistance training, you're going to be looking more at those basic sets, 3 sets of 10 reps with a rest in between. So that's going to be looking at helping to develop your lactate tolerance. And also when you think about circuit classes, that's a good example of sort of quite high intensity, but short recovery to try and improve your lactic acid removal. So circuit classes, and also that idea of sprint repeats. So for these ones, it's having that much shorter recovery. So the body's having to learn how to remove that lactate faster. To be able to fully recover, it can take up to an hour for that full removal of the lactic acid from the blood. Right, so the third system is your aerobic system, and this is used for those much lower to moderate intensity activities and longer duration. So basically, once the lactic acid system runs out, you're going to be looking at entirely getting your energy from the aerobic system. Much slower to kick in, takes much longer, can't generate as much force and speed and power, but it can last much longer and you don't get any limiting side effects. The aerobic system is obviously aerobic, so you're using oxygen within it, and the ATP is generated in the mitochondria. So the more mitochondria you've got, the more ATP can be generated. And the energy is supplied by the glycogen, so the carb stores, glycogen, and by fatty acids. If you remember, we said that proteins are only used when these other energy stores have run out. And the byproducts we get here, as you can see, are carbon dioxide and water. So the energy provided from the breakdowns of your glucose, your fats, and your proteins provides the energy to convert ADP back into ATP. It's actually an incredibly complicated system, the aerobic system, and there is a section in the manual that describes a little bit about kind of the Krebs cycle and various other parts of it, the citric acid cycle, but you don't need to know that. It's quite interesting, but basically it's just knowing that this is a system that's sustainable over many hours. You imagine going out for a long walk during the day or a long jog or a marathon. This is the kind of thing that's going to be used for the aerobic system. And it's actually it can produce large amounts of ATP, but it must do in the presence of oxygen. Fats can only be used with oxygen, can only be sort of burnt in the presence of oxygen. So as I say, the proteins only in the absence of sufficient carbs, and the main byproduct is that carbon dioxide. So when we train our aerobic system, we're looking to improve our body's ability to take up and use oxygen. And to be able to do that, our body over time increases the number of capillaries we've got, so it can carry more blood, so it can carry more oxygen to our tissues. We produce more mitochondria. We're able to metabolize our fat more efficiently because that produces a lot of ATP. We get more glycogen and myoglobin stores actually within our muscles themselves. Our anaerobic threshold is raised, and overall our cardiorespiratory system becomes more efficient, so we have more blood volume going around our body. The stroke volume increases as our heart gets stronger, increased cardiac output, remember, over a minute. And the overall impact is increased CV strength and endurance. So when we're looking at training the aerobic system, we're looking at doing this at around 60 to 75%. And we're looking here at activities at a lower intensity, a low to moderate intensity, and it must stay below that anaerobic threshold, remember that OBLA. So examples of this are a run of 2 minutes at a moderate to high intensity, followed by 2 minutes at a much lower intensity. So it's still an active recovery, and then just repeating that moderate intensity to lower intensity for 30 minutes. or changing that to 30 minutes or more of any low to moderate activities such as cycling, swimming, long distance running. Fill in the blanks of the kind of activity you like to do there and just that ongoing intensity. Okay, so let's have a little think. What I want you to do now is to, in your own time, to take a moment to stop on each of these slides and go over in your head. You may want to write it down, or you may want to do a mind map, whatever works best for you. Think about that phosphocreatine system we went through first. What kind of exercise do we use it for? How long does that system last? What's the fuel source for that system? How long a rest do you need? What waste products, if any, are produced? And what is the response to training? What intensity do we need to train it at? So have a little go at writing those things down, see what you can remember. So again, now have a look at that aerobic glycolysis system, otherwise known as your lactic acid system. Get your piece of paper, create your mind map. What kind of exercise is this for? Again, how long does that lactic acid system work for? And what is the fuel source that you use for it? How long's needed to fully recover from that? And what are the waste products and what's the impact of those waste products? Have a think about how would you train the lactic acid system? What percentage should it be trained at? Think of some examples. And then finally, you've got your aerobic system. Again, what are the examples of that kind of exercise? How long does the aerobic system keep working for? What fuels are used? And in what order are those fuels used? Think about rest times needed. And what, if any, are the waste products and the effect that would have? And the response to training the aerobic system. So what sort of percentage should you be working at to train the aerobic system? And what are going to be the physiological adaptations to that? So I hope that was helpful. I hope you took some time to do that activity at the end. So now you should be able to identify which energy systems are used according to the type, the duration and intensity of exercise. And remember that graph at the beginning, looking at how they all interact. Secondly, you should be able to tell me about the byproducts of the energy system and how these can affect performance. And thirdly, explain the different types of training on the production of fuel for exercise. So I hope that was helpful. Do take the time to go and do the quiz associated with this. You'll find some questions. I'm sure you'll have some access to past papers. So it's well worth doing these to see the kind of questions that you'll be used. Again, the quiz does actually use a lot of past paper type questions. So please do that. Have a read through of your manual. Don't forget, look at those interactive revision tools, and congratulations, because you have now been through the whole programme of the Anatomy and Physiology Level 3. So I hope you've enjoyed it and learnt a lot from it, and I hope these videos have been useful. Okay, all the best with your revision. Thanks very much. Bye-bye.